Okay, everybody, I'm going to get started today. We can all finish up conversation. So I guess I've announced a few times. I sent another email and another Slack announcement, and I'll do another announcement in class at the midterms Thursday. Some of you are not in this room. Most of you are in this room, but of course the people I emailed and sent a calendar invite twice, they're in another room over in Jack Baskin. So please go to the appropriate room for your exam. I believe it's 156 Jack Baskin. Okay, this is just so we have plenty of space because otherwise every seat in here will be full, and we don't want that. Question?
How were the people determined to go to the open room?
I sent invitations to go to the room.
Oh, like, how did you pick them?
I picked them in an algorithm that I decided, so it doesn't matter. Yeah, no, I memorized where everyone sat here, and I picked your neighbor, invited your neighbor to the. No, I'm joking. Now, in terms of announcements, so I know Hodder was gone on Monday, so didn't have Opstar, so I've asked him to have a review session tomorrow. He hasn't told me what time yet, so hopefully this will work out. Keep an eye out in the Slack announcements. We'll announce that. Unfortunately, I have 127 meetings and other meetings almost all day. I have a little bit of time in the morning between, I think, 9 or 10 and 11 if people want to schedule meetings for questions. But other than that, I'm pretty slammed with my courses. So yeah, I think other than that, I'm not going to make too many announcements on the exam. Other than I'll show this again. How do you study for the exam? You should have been studying all along. You should be doing your homeworks. You should be going through them. You should be looking at the solutions and figuring out where you made your mistakes now and why you made your mistakes. So I posted the homework 3 solutions this morning. There was one discrepancy. There's, I think, 2. One of them was that the slew rate I used is when you give a slew rate in SPICE, it's actually the 0 to 100% rise time, whereas in the lib files, it's actually 10 to 90%. So that's a slight difference that could cause some mismatch in your results. I wasn't really going to dig into it too much, but that is a mismatch by a small percentage. Other than that, I think there might have been one more related to indexing the table, but I can't remember exactly what it was. So please let us know if there was a mistake so we can fix that. I suggest you ask people questions similar to this. Also, go back to my slides. I give lots of examples in the slides. You should look at them without my explanation and see that you know how to do them. I think there's plenty of examples in lecture. So you can also look at the 2 textbooks. There's examples of problems in there. But as I mentioned quite a few times, they emphasize different things than I do. And so there may be a lot of questions that I haven't covered in class. And there may be some that I cover in class that they don't. So I think there's a difference there. Yeah, so I will leave that at that. Now, and lastly, it covers through, one more announcement, it covers through lecture 6, including lecture 6, which is CMOS gate delays. Interconnect stuff and this buffering lecture are on your next midterm, which is in 3.5 weeks. So I split it up so you have 2 separate midterms intentionally to kind of divide stuff up. And also on the exam, you're allowed 1 8.5 by 11 sheet, both sides, handwritten only, no printing with a printer of any sort, even if it's a diagram, especially no printing of my slides. And you can also take a calculator, but you can't use a calculator app on your phone. So you can use a calculator. All right, I think that's all of the announcements. And yeah, look out for the review session from Hodder, which will be announced shortly. Okay, now we talk about buffering. So we talk about mostly delay of gates, delay of interconnect. Basically, and you've used logic synthesis in 125 where you can basically factors equations and tries to minimize logic, right? How do we deal with the wires? I've showed that scaling, basically the wires go crazy and those delays dominate gate delays, so what happens? Well, starting in the 90s through present day, there's something that's called physical synthesis. All commercial tools do it, the open source tools that we're gonna use do it, and what this is it's physically aware logic synthesis. And so physically aware meaning wire aware. It cares about where you place things and it approximates the delay of the wires so that you can account for that when you do your logic and other optimizations. And if we see this in the open road stage, this is actually done at multiple steps of the design flow, which I haven't talked about this design flow yet. This is coming up in a couple lectures. But basically we have the library stuff and logic synthesis on the left. We go through a floor planning stage where we divide up the chip area into blocks. We go through placement where we place the logic cells, the library cells. Clock tree synthesis, which we'll talk a little bit about coming up. Routing of the wires, then we actually know how long the wires are and what their delay is. And then finishing, which is your final checks and so on. Now, this physical synthesis step actually occurs along the way in a number of these stages. It can occur during floor planning when you're dividing blocks up because you then know a coarse level of where things are. It can be during standard cell placement because you're then determining the length of wires based on this gate I'm driving is this far away. But you don't know which level of metal, you don't know exactly where the wire routes, so you don't know exactly the R's and C's associated with that wire. And then with clock tree, you then know your clock and any skew you have associated with it. And then finally your routing, you actually determine the layers your wires go on, the exact number of tracks and detours they take to have everything route. Basically you do this because you have more impact in your timing the further left you are. You can make decisions early. But you have more view of what your wires are going to be when you go left. You know your actual wires and layers and the actual delays, so you can fix them. But then things get harder to fix. Right? If you have it placed, you have all your routing done. In order to fix anything, you have to unroute it, move something, reroute it, and that gets complicated. So you want to make decisions early to have kind of better results. Now, there's a number of steps that are basically called physical synthesis moves. So by the way, I've been adding to the Open Road project. I was contributing, I kind of refactored their code so that it has an idea of a move. And these are the current moves in Open Road. They're very similar to a lot of commercial tools. Actually, I added the one on the right bottom size down recently. Swap VTH was also added. These are basically local changes to a logic netlist to improve timing. You can think about it as, on the far left here, it can be anything from refactoring or De Morgan, so changing your logic. If you change your logic, you might end up with more or fewer inverters, right, based on De Morgans. And that can improve your timing. You can do things like cloning a gate. Instead of having one gate drive 2 places, you might be better off making 2 copies and putting those closer to the destination, or split the difference in the location from the source to the destination. You can do buffering. You want to add buffers to wires to improve delay. I'm going to talk about that today. That's one of the most fundamental optimizations. Split load, I'm going to ignore. This is a primitive form of buffering. You can also move logic gates. If, let's say, you have a really long wire, you might want to move your gate halfway between where it's coming from and going to. That'll improve delay. You can do things like sizing of gates, increase the drive strength, which lowers the resistance, and then it can drive the wire and the fan out better. Sometimes you want to unbuffer it. Maybe it had a bad buffering or something relocated and it made it worse. And so you want to unbuffer it and maybe try one of these other optimizations to make it better. And then also things like we saw in the homework, swapping pins. We saw that different input pins to a gate have different delays. So if you have a gate that has the same function for input pins, you can try the other input to improve the delay. And then sizing down and swapping the threshold voltage because lower threshold transistors, which sometimes you'll have a library gate with that, will be faster but higher power. And so the point is, these optimizations basically are physically aware synthesis, right? You're redoing the logic either by moving it, buffering it, or sizing it according to the wires. And it's done iteratively. So it's done during floor planning all the way to your routing. And the way the tools work, they basically try a lot of moves, and they have heuristics to make the moves. Those of you that know Aaron, who's a TA for the 127 class, he's using machine learning to do some of these things, like which moves to apply, and so on. That's kind of the current state of research on this topic. So this is, I should mention, I actually worked on the sizing, size up, size down, as far back as when I was at IBM, many decades ago. And so this has been a problem, and it's still one of the main tools to get timing convergence. So today we're going to mostly talk about buffering. We're going to talk a little bit, we're going to talk about two types of bufferings you generally do. We're going to then, I might skip over some of this. We'll see how we go about generalized buffering problem, but I'm going to give you some intuition into why to buffer things. Now, you may ask, if the tools do this, why do I need to know it? And the answer is the tools can be constrained by the problem you give them. For example, one common thing is if I have a big block, say a memory, and I want to buffer a signal going across that block, I can't put a buffer in the middle of the memory. And so it ends up putting a buffer nearby around the perimeter of the memory. That's an example of something where it can't buffer it well because you gave it a bad floor plan. And so as a designer, you need to go in and recognize, run your static timing and say, this is the stage that's bad. Why is it bad? Oh, there's a big detour. It goes around this object, and I need to fix that. So it can fix it through one of these things: relocation, buffering, cloning, etc. There's a reason it's not finding that and not doing it appropriately. So it's more about diagnosing problems and understanding why you may want to change things to solve this problem. I'll give kind of this is one of the best known buffering algorithms. Van Ginningen, I'll talk a bit about that. This guy was originally on my PhD thesis. He was not on my final committee because he founded a company called Magma, which is out of IBM. They got bought by Synopsys, and does a lot of the Synopsys tools now. And there was a copyright suit where he took a lot, or patent suit where he took a lot of the ideas he came up with at Synopsys, started a company. There's a bunch of lawsuits, and then they bought the company and all this stuff. So he was kind of, I don't want to say in exile from the community, but he was no longer working when I defended my thesis. But he did a lot of interesting things, and this is an interesting algorithm to see kind of how you approach some of these problems. Every one of these problems is a CS optimization problem, really. And formulating it the right way that's tractable is a very interesting problem. So let's start out with cascaded buffers. Now, first, by the way, this is one of the most common interview questions in VLSI, and we'll now learn the solution to this by the end of this lecture. I've been asked it at least 4 or 5 times as an undergrad. Now, how do we model this? Okay, now if we have something like on the left, we have a buffer. Now, a lot of times I'm going to say a buffer. This could also be an inverter. We frequently ignore polarity, and we'll assume that we fix polarity by either correcting it at the receiver or the start. So these can be kind of interchangeable. But if we have a buffer, and in this case driving capacitance C out, how do you find the delay of it? Elmore delay, right? And so we're going to use an Elmore delay model, except we're going to add a couple parameters, okay? The first thing is, when we do sizing, actually, let me go back to one slide I might want to review when we talk about gate delay. When we pick sizes of gates, remember we picked all of these ratios to kind of equalize rise and fall delays. But remember, we can scale the gate by scaling all the transistors proportionally. So when we have our library, we have an inverter 1 and an inverter 2, we scale up all the transistors by 2x. Or we scale up all the transistors by 4x. And this decreases the resistance of that gate by a factor of 4, right? Because just the output resistance of this gate depends if we're pulling up or down, but it's either the pull-up path or the pull-down path of our worst path of the logic gate. Same thing applies to NAND gates, NOR gates. We scale them proportionally. So now we can basically refer to a gate as a size S. Okay? So I just want to kind of, I think I skipped over that slide or went over it very quickly and remind you of this. Now, this applies for our inverters and our buffers as well. Now, and just to kind of emphasize, it could be an inverter. A buffer is made by having 2 inverters back to back. Okay? Now, when we look at this then, the electrical model of this is what's on the right, where we have R, and this is actually R divided by S. Because remember, we scale up the size by a factor of S, the output resistance goes down by a factor of S. Just a linear equation. Because we're scaling up all the widths of the transistors by a factor of S. The topology doesn't change for a given gate, it's fixed. So that resistance scales by that amount. But remember, when we have a gate, we also have the resistance of the gate itself. When we draw the layout, remember we had the 2 drains connected to the output, and there's the perimeter and the area of the drains, and that adds capacitance to the gate. Right? When we draw a gate like this, we have poly like this, we went over this computation of figuring out the perimeter here, figuring out the area here, and this all adds to the capacitance. And what happened when we increased the size of this? Well, we increased the capacitance. What we assume here is it roughly linearly increases the capacitance. That's a little bit of an assumption because it doesn't really change kind of this one dimension here, but it's close enough. So when we increase the size of a gate, or in this case not just a transistor but an entire logic gate, that internal capacitance goes up by a factor of S. Right? All the sources and drains go up generally. That's this term right here. That's increasing the size. And then we have our output load, C out. So this is whatever wire, whatever fan out we're driving. And this is basically the component that formulates the delay of this gate, right? So we have now just Elmore delay. Again, it's just R times this is all C, and this approximate is because of Elmore. So we say, okay, 0.69. Approximate if you drop the constant, just say it's 1. So Elmore delay model. But this Elmore delay model includes the size component of the gate. Now, I'll point out one other thing here. What I just showed there is roughly the kind of the right of this figure, right? This corresponds to the delay. There's also the left of this figure right here, which this says the input of a gate has a capacitance here, which is also proportional to the size. Because remember, when I drew this thing on the lower left, I drew the green capacitance here. This becomes CP. I should just have it in green. But then we also have this component here, which has the overlap capacitance and the gate capacitance of the actual gate of the transistor itself. So you have an input driving the polysilicon, and then the output comes from this diffusion and the other transistor as well. So the input capacitance of the gate also goes up right here. It also goes up proportional to the size of the gate S. So if you take a 1x inverter and you double it to a 2x inverter, the input capacitance goes up by 2x. Or if you take a NAND 2 and go size 1 and go to NAND 2 size 4, its input will go up by 4x. But the starting input capacitance is different for both of the gates, right? That depends on that previous slide we showed in the library lecture. What is the starting capacitance? It's this, right? So for an inverter, the starting capacitance would be in A, which is a size 2 inverter and a size 1 inverter. So you can call it 3. if we look at a NAND gate, these are connected together. What is the input capacitance of that? Well, it's going to be a size 2 PMOS and a size 2 NMOS. This is going to be a size 4. So it's going to start with 4. If we go up to a size, with S equals 1, that's 4. If we go up to S equals 2, a size 2 gate, it's going to be 8, right? Scales up linearly. We're going to revisit this for all the logic families coming up when we actually do gate sizing. So right now we're mostly just concerned about inverters. So we have this kind of linear gate delay model. Now, why do we care about this? Well, the nice property of this is two things. One, an inverter is actually very good at driving big capacitors. It's actually the most efficient gate, right? An inverter or a buffer. Because as we showed, in NAND 2 and NOR 2, you start stacking transistors, they become slower. You have to scale them up and have more transistor area to make them have the same drive strength as an inverter. So they're inefficient. Whenever you can, you want to have a buffer or inverter drive a big cap or a big wire. Second of all, there's this kind of interesting property here where the way I drew this here is I separated these into two things, kind of the driving part of it and the kind of input part of it. They're actually very good at decoupling the delay. What do I mean by that? Well, remember when we look at a wire and we said we calculate the Elmore delay of a wire, how do we do that? We take the R and you multiply it by what? Like if you have a tree, what did we do? You multiply it by all the capacitors in the fan-out. Well, what this does is this says I can actually stop that and say don't multiply it by all the capacitors in the fan-out. Stop right here at this inverter and only if you have something driving this, only drive the capacitor on the input of this gate. I essentially decouple it from all the downstream fan-out and that will not affect the delay into this gate. Yeah.
Why don't we do that for everything? Just not have Elmore delay exist?
That's a great question. Why don't we do this for everything? You can't put buffers everywhere. Actually, they're a good point though. At IBM, when we started doing this, say in the 90s, early 2000s, how many gates on a chip do you think are buffers? It started going up. As wires got more significant, it became more and more and more. A modern chip can have as many as 70% of the logic gates that are just buffers. That's not good. What is that doing? They do no logic computation, right? They just restore a signal electrically or isolate it from the fan-out. You want to use as few of them as possible. And so that's why this is an important optimization, right? You want to use much less than 70%. That's for a high performance goal. I'm hoping in our designs will probably be like 20% or less. That means you have short wires, you don't need buffers, and that's a good thing. So yeah, that's the answer. You could put a buffer everywhere, but then suddenly you have an extra buffer or 2 or 3 for every wire in your design, and that's very inefficient. Now let's go over the two kind of use cases of this and why we use the buffers. Now remember I showed this plot when I talked about gate delay. This also comes into play because we can now see this plot again in terms of the context of the self-loading and this new equation we had. Again, this is just Elmore delay, except I factored out two things. One is the Cout, which is your output capacitance, and one is that S times Cp, which is the self-loading term due to the gate itself. I make the transistor bigger, or the gate bigger to drive more, but I make its own capacitance on the output more, which kind of it also has to drive. And so that's why we see this component here, where this asymptote you're going to find, down here, is actually going to be R times Cp in terms of Elmore delay, right? This is delay over here, and it's going to approach that value. Because what happens is Cout stays fixed. I'm not changing what I fan out to. I'm going to keep making S go up and up and up. But luckily, R over S cancels out with the S times Cp, so that just becomes R times Cp. This is essentially the limit of this equation as S goes to infinity. You can never do better than that. And then we have another component of the delay, which if you kind of factor out that component and say the other component of the delay is R over S times Cout. As the S goes to infinity, that term goes to 0 essentially. R over S becomes almost 0, and it becomes insignificant. So that's why we have that asymptote, and that's why it exists because of the sizing problem. This is for a single logic gate, or a single buffer driving a load. Now, intuition check. What do you want to do? Let's say we have one Cout, and we want to drive it more efficiently. What do we do? Well, you make it bigger, right? Let's say we want to make it bigger. The one on the left, let's say this is for size equals 1. What is the delay of that equal? Like, and again, we have an equation over here. What is that delay in terms of Elmore delay? We figured it out, right? It's R over 1 times Cp plus Cout. Which, what is that? That's just R times Cout. Or R Cp plus R Cout. Right? Now, what if I were to size this up to, say, a size 100? Or let's just say size 2. What happens to the delay? Well, here go ahead. What do you think? It has because of the R going down. Yeah. What we're assuming here is that Cout is significant compared to Cp. That's the big question. So if Cout is much bigger than Cp, I'm going to get half the delay. It's going to be half. This goes along with our Elmore delay thing, right? If we decrease the resistance by half, R times C goes down by half, right? So as long as Cout is big, that holds. What happens though on the input here? We mentioned that input capacitance. We have this other part of the model. Yeah, go ahead. Here's the key observation. What does this input with the question mark look like? Well, if I just let's say I made this a size 100 gate. What is the input capacitance? Now remember, that's this term right here. I'm ignoring that in this equation I just computed. So the bigger question is, what's driving this? Well, presumably it comes from somewhere else. Maybe there's another gate over here that drives it like that. It's the same one here. What happens to this delay when I make this gate a size 100 gate? The delay goes up by 100 because it linearly affects the output capacitance, so it slows down the previous stage. Well, that's no good. I made this one, twice as fast, but I made the previous one twice as slow, let's say. So what do? I can never win then, right? No.
Just to clarify, you scaled the blue capacitor, or you scaled the blue delay up by 100, so it's slowing down.
So let me take a step back. So let's say I kind of conflated two examples, the extreme one and then this 2x one. Let's say I increase this gate to a 2x gate. That means that this capacitance goes up by 2. What happens to this delay of this gate here? That one goes up by 2, because now instead of RC for that gate, I have R times 2C.
Oh, the output capacitance of that gate. Okay.
Yeah, because the output capacitance of that red gate is the blue gate, which just doubled, but I have the same size red gate. And so since the output capacitance doubles, the delay doubles. We have a conundrum here, right? You have to solve this problem. Well, the answer is you don't use just one stage, and you have to do something more optimally. You have to do what's called a multi-stage driver. And basically every stage kind of is going to ramp up the drive strength to a bigger value. Now, what is the ideal ramp up and how many stages? Well, that depends on what Cout is. Okay? If the output capacitance is very small, well, you probably don't need a buffer. If the output capacitance gets above a certain value, you might need one buffer, but you probably don't want to. It's not a big buffer, so it probably doesn't matter too much. If the output capacitance is giant, you want to have, say, 4 or 5 stages, and each one gets bigger so that you compromise the drive strengths for the input capacitance of each stage. Yeah.
So then to when you have fan out fours and CL.
I don't want to talk about fan out yet because that's a different problem. Yeah.
Are the buffers usually placed close to the source, or what's are they spread out along?
You're getting to the good questions. Where do we place these? Let's assume they're all at the same place. So this is actually kind of ignoring the wires too. I'm going to talk about that too, because that's another problem. Fan out and long wires are two separate issues in buffering. So let's assume that the wires are insignificant here, which we know is bad, and you're trying to just have a big capacitance. Well, what we're going to find is that if we call this ratio rho, that's the Greek character, there's actually going to be a fixed ratio of every stage to get you to that answer. And how do they do it? Well, essentially what they do is they take that equation I just showed you. So this is the same one right here. And I approximate every stage as that. And then I take a derivative of it. I'm not going to go through the math, but it's first year calculus. I take the derivative to give us the minimum delay. Because if you think about it, if you have an input driver and output load, there's an optimum size that trades off the delay of the blue gate for the delay of the red gate. Right? If I make the blue gate bigger, it slows down the red gate. But if I make the blue gate smaller, it speeds up the red gate, and so on. And so what we're going to find is that this is actually a quadratic. There's actually a minimum. And calculus is good at finding minimums and things, right? So I won't go through the math, but basically you find a derivative of this whole thing, the delay of the thing, relative to rho. And so I did exactly this formula. I took that and I made S scale up by rho every stage. So if the first one is size 1, the next one is size rho, the next one is size rho squared, and so on. So if this is 1, then this becomes rho, then this would become rho squared, and so on. And then I write the delay for each of those just using that same delay model. So it ends up being a quadratic equation with a minimum. Again, I will not put that on the test, but the intuition is useful. The point being, the actual solution is very simple. If I take the derivative of that, I end up with this equation. This is called P inverter plus rho times here. What is this component right here? Well, that is R times CP. Remember the previous equation I said? Oh, if the output cap, that's the self-loading part. So it's the self-loading part of the delay, which is actually constant for any inverter. And then there's this other term. It's rho times 1 minus natural log of rho equals 0. Because the derivative, we're setting the derivative equal to 0. And you can see there's a natural log there because it was an exponential increase in the sizes. There's rho squared, so it's an exponential series. So that's why you have a log when you do the derivative. What is the solution? Well, there's two possible solutions that are easy. One is let's drop that P inverter part and just assume it's 0. That's maybe not a good solution, but it is a solution. If you do that, it actually comes out that rho should equal the natural E. Makes sense. We have a natural log, and E is usually involved in natural logs, and so that's the solution. But if we assume that rho is some other value, let's say 1, you end up with something like 3.5 or 3.6. The good news is this exact value doesn't matter too much. I always just assume it's about 3. And what we'll show is that when you actually use a value of 3, your answer is actually pretty close to the optimal. You can pick 4, you can pick 2. It's all about the same. It's probably within like 15%. The reason being, we're already not considering wires and all these other assumptions, so that doesn't matter too much. So what does that mean then? Well, let's think about a capacitive load here. By the way, I put a paper on our website for reading. This is a paper that's called The Method of Logical Effort. And one of the things it does is it starts with this example and it works on to other cases of other logic gates. And these examples are actually from that paper. So there's a PDF on, I believe I already put it on Canvas. And that is required reading. It's a short paper, but everyone should read that assignment. Now, let's say we want to drive some big capacitance. And we're going to say a fan out of 64. Now, what is 64? Just say it's farads, femtofarads, doesn't matter. All of these numbers are relative to some term. And that term is usually the input capacitance of the smallest inverter. So 1 means the input of the smallest inverter. 64 means 64 inverters, right? Input capacitance. And so when we also then kind of say, okay, well, what is the size of a gate? When you say the input capacitance, you also know what the size is. Because remember, the input capacitance, C in, is proportional to S times C gate plus C overlap, these terms, right? So you can say, well, if C in is 1, that's roughly S too, just by a factor. So we kind of use these interchangeably. Now, if we want to do this, what we can do is say, okay, well, let's just enumerate, right? If we had one inverter, and again, we're going to ignore polarity here. So it doesn't matter if the output's inverting or not, we can fix it later. If we have one inverter driving a capacitive load of 64, what is the delay? And here's where we can use kind of our simple formula with unit delay, and we can say, okay, again, this is going to be R times 64, and R is going to equal 1. Actually, let me do it this way. I want to keep both components, so we're going to basically be using this equation back here. So it's R over S times S over S times P. So we're going to keep using R over S times CP times C out. And so if we have size 1, what is the delay going to be? So we're going to assume it's going to be, basically, it's going to be R times CP times R times C out plus. And how do I want to explain this? So this is, we're going to assume, in this case, that this term right here, we're going to assume that R is 1, because again, we're using the input capacitance and the size interchangeably. This is essentially going to be 1, and then this term is going to essentially be 64. So this is substituting R equals 1 for this gate, because the size is 1 gate. And that's how we get 64, okay? Now, what if we have 2 inverters? Now, what is the delay in the second case? Well, what is the delay of the first stage? Well, it's going to be, first of all, R times CP of any gate is going to be 1. Any inverter is going to be 1. It doesn't depend on the size. So what's the delay of this first stage here? It's going to be 1. Plus, what is the delay of this size 1 gate fanning out to the size 8 gate? It's going to be 1 times 8, which that's going to equal 9. Okay? So just assuming R is 1. Now, what is the delay of the second stage? Well, it's going to be 1, because that's this parasitic part of the delay. It's the same for all gates. And now if we have a size 8 gate driving a fan out of 64, the R has actually gone down. It's going to essentially be the ratio. It's going to end up being 1 times 64 over 8. Now, why is that? Well, the 8 affects the resistance. Remember, R over S. So the 8 is in the denominator for the resistance. Actually, let me write this way to be more clear. The R part is R over 8 times 64. And then we assume R is 1 again. So it's 1 over 8 times 64, which gives us the delay of the second part, which is 8. And so what is the total delay of this then? Well, it's 8 for the first inverter and 8 for the second inverter. Sorry, 9 for the first inverter plus 9 for the second. So they dropped this first 1 for each one. So it's 1 plus 8 for the first inverter, which is 9, and then 1 plus 8 for the second inverter, which is also 9, which gives us 18 here. So if we generalize this, every stage is going to be basically equal to a delay of 1 plus rho. Here, if it goes up by size 4, and say the 3 inverter case, the first inverter is going to be delay of 1 plus 4, or 5 total. Same thing for the second inverter and the third inverter. They're each going to have a delay of 5. Now in the fourth case, what is the delay of the first inverter? It's going to be 1 plus 2.8, or 3.8. That's going to be the delay of each stage. Now, what happens here is, if I go through and enumerate this, one of these is the fastest, right here. So this one is 15. It's almost the same as the one over here, but adding an extra inverter doesn't give us that much more improvement. So here, 3 is the best number of stages for this gate. So I just kind of enumerated, tried them all. I use this RC model, and I say, okay, what is the delay kind of doing this kind of by hand? Now, this is the computation. So they can also do this derivative with respect to the number of stages. So this previous thing, I said, what is the best ratio, rho? This is now saying, what is the best number of stages? This will then also get us the, actually, I was wrong this previous time. This is how you get rho. This is not correct. This is how you get rho. This is the derivative you set to 0. And this gets us that equation of, the P inverter plus what I had back here. Rho times 1 minus natural log of rho. Is that it? Equals 0. And so this then says, okay, the 3, how do we get to that right number of stages? Well, to figure that out, you basically take the log. So think about when you have a binary tree. How do you find the depth of the binary tree? You do the log base 2 of the number of leaves. That gives you the depth of the tree, right? We do basically the same type of thing here, where we say, how do we divide this up into a number of stages? Well, let's take our optimal number, our optimal rho. Again, that can be E, it can be 3, it can be 3.59. Take log 3 of the number of the capacitance to get that number of stages. So all of these end up being around the same. And so in this case, the log, base 4 of 64 is about 3. And that gives us the 3-stage inverter as the fastest. So the point is, we don't have to actually try all of these. We can just say, however much capacitance we want to drive, if I take the log, in this case base 10 of that, that'll give us the number of stages. And then what are the sizes? Well, every size is scaled up by rho. So it gives us that scaling factor. Now, so I didn't present this the best way, but it's going to become more clear as we do more examples on this. We're going to start talking about it with general logic, and now we're going to also apply this to wires as well, because in practice, this is not super useful. How often do you drive a giant capacitor with no wires? That doesn't exist, right? In general, if you have a giant capacitance, it's going to be a wire branching throughout your chip to do a lot of different things. But my point being, this is something that's called the exponential horn. And this is a common interview question of just how do you size these up. And it's an exponential horn because you keep increasing the size of the gate to drive a large output capacitance. And here's the book it's actually a book as well as a paper. This is the book, but I gave you like a short paper version that talks about the most useful stuff for the book. The book doesn't actually have that much more material in it. It has a lot of examples and stuff, but I'm not requiring the book to be read. Now, so let's talk about wires. Now, this is actually the case where I talk about wires dominate delay. We're actually going to use buffers in this case, but we're going to use them in a different way. We're going to use them in a way that we call it a repeater. And the idea is they're going to break up a wire so that we have 2 segments of wire instead of 1 wire. And remember how I said that the input capacitance of a buffer is separate than the output drive? It kind of stops the delay of the output stage from affecting the input stage. And that can be used to make longer or faster wires. And then I'll also talk about generalized buffering. This is with fan-out, because we don't frequently have one gate driving at one other output somewhere else on chip. Usually there's a fan-out of 2 or 3. So usually just driving a single output doesn't make sense. So we already talked about this. This is a repeat from the previous slide. We've seen as you go down in technology generation, transistor delay is going down, wire delay is going up. Brief review, why? Yeah, the capacitance. Which type of capacitance, right? We have the capacitance to the bottom and the capacitance to the sides. And so we have this trade-off. We want to make the wires taller so that they have less resistance, but then there's more capacitance to the sides and the bottom. So they end up getting slower anyways. But if you make really fat wires, they can be fast, but you try to make them as small as possible, they're slow. So that's the problem. Now, the other thing I mentioned as I talked about the different types of global wires, local wires, kind of intermediate wires, the biggest challenge to this whole wire scaling thing is this delay with interconnect delay going up is essentially for the local wires. If I have my metal 1, metal 2, those delays don't scale. And this is because of all the geometry stuff. This is just drawing another way what I talked about previously. But basically, if we scale our technology down by a factor of s, now this is not size, this is the geometry component. Let's say we go from 180 nanometer to 130 nanometer. That would be scaled down by a ratio of 130 over 180. Okay? You can't just shrink all the shapes by that amount. It doesn't work. We saw an example with interconnect, but also with transistor links, that doesn't scale linearly as well. But what we see is that if we scale that, wire delay ends up scaling, the resistance ends up scaling up by a factor of s squared. If we decrease the width and height of the transistor, or of the interconnect, sorry, the width and spacing of the interconnect, it goes up by a factor, resistance goes up by a factor of s squared, down by a factor of s squared, but the capacitance actually ends up staying roughly the same. But then the kicker is, so resistance doubled, sorry, because s is less than 0, so r over s squared is 0.7 squared, right? So that goes up. But the scaling of the height and spacing ends up canceling out, so the coupling for these local wires doesn't change. But what happens, why do I keep saying, oh, long wires are a problem? Well, the problem is the length doesn't go down. If we were to shrink the entire chip down and only not put any new transistors on it, the wires would get shorter. But what do we like to do with chips? We like to put more on the chip. So what happens is chips stay the same size, or in the case, as we've seen with NVIDIA chips, they get bigger. I used to call a big chip a centimeter by a centimeter chip. We talked about the first day of class, NVIDIA chips are now 2 centimeters by 4 centimeters. They used to have centimeter by centimeter chips 30 years ago. Now they're bigger. But that's because we're fitting, however many 100,000x more transistors on them. And the point being, the long wires don't get shorter. The long wires stay the same length. Those are the ones that end up being a problem. Yeah, the global wires don't matter. The local wires will go down a bit because we've decreased cell sizes and all this stuff. But going far doesn't improve. Now, we want to talk about kind of like we formulated with the buffer. We can formulate the RC delay of a wire. Again, this is going to be Elmore delay, which again, R times C. But we talked about what the resistance and capacitance are. If we have a wire, in this case, of length L, and assume it's a fixed width, what is the resistance of this wire? Well, the resistance of the wire is going to be R times L. And what is this R? This is basically, remember I said that the resistance was actually R over W times L before. But I'm assuming this is a fixed W. So this little r is kind of a fixed value of the width. And so that doesn't change, we're not changing the width anymore. So it's basically per unit length. Or another way to think about it is, that's my square size. Remember I talked about R square? That's the square size. And so we know the resistance is R times L. Now what is the capacitance? Here I'm going to basically lump together the fringe capacitance and the area capacitance into one term. Because I'm not changing the width, I don't really change the area separately from the length. So the capacitance of this thing is going to be equal to the little c times L as well. This includes both area and fringing capacitance. So it's just in terms of per unit length. Now, if we multiply those and solve them, we end up with the delay, in terms of Elmore delay, is RC. This is a term that's basically the unit wire delay. So it's a delay of a wire per unit length. So it's like a ratio delay. And what that scales as the L term actually goes up quadratically, L squared, because it makes it higher resistance and higher capacitance. So wires get slower with the square of the length. That's a problem. That's a big problem. Now, if we include local interconnects, which local interconnects basically, we scale down the width. So the width goes down. So that means the resistance doesn't, we make them taller. So the resistance doesn't quite scale the same. And then they also scale like this. But the global interconnects, we basically make them fatter wires, taller wires, and so those will actually go down. The delay is doubled, which is a problem. Now, the whole point of this is I want to get to this next slide. Like we could have, I don't want to talk about scaling too much, but what can we then model the delay of a wire? So we've already talked about R times C, but let's model this with a single wire of length X. And we have these component terms. R is the unit resistance of the wire, and then C is the unit capacitance of the wire. So here, this right here is the resistance of the wire of length X, and this is the capacitance of the wire of length X. And then why is it divided by 2? Well, here I'm assuming this pi model, right? So there's a factor of 2. I could ignore that if I wanted to use just the old-fashioned RC model like this. That would get rid of the factor of 2. Then what is this term? So this capacitor right here is due to the wire itself. So that's why you have R times the capacitor of the wire itself. We also have a fan-out capacitance. We can call it C. We can call it C out to be clear. That is whatever gate, for example, might be here. That'd be like the input capacitance of that gate. Well, we also have this term of the resistance times that capacitance. Because remember, we multiply the resistance times all of the downstream capacitors. I can rewrite this in the other way we did in class, where we could say XR times XC plus C out, right? And that would be the same value, right? Because this is all the downstream capacitances. But then we just distribute that XR term. So this is the delay of a wire of length X. Now, when we have a buffer, we know the delay of a buffer is going to be related to the size of the buffer. Let's call it the resistance of the buffer, and we're going to assume just buffer B. So let's call this R a function. The delay of this buffer is going to be R times C, the R of the buffer. And then the input capacitance is going to be the input capacitance of the buffer. Now remember, this was essentially R over S before, and this is essentially S times C gate plus C out overlap before. We're called CP, whatever. So this is kind of those linear scaling things I said. But now we're just saying, oh, there's a buffer B, call it some size, and it has some fixed value. So we're just making a function of that. The point being, what we can do is, if we have, for example, a buffer driving a wire. So here, that buffer B is going to have an output resistance R of B, and it drives a wire of some length. That's going to have a resistance and 2 capacitances. So this is again using a pi model. I could do the same thing except get rid of C1 and only have C2, but the pi model is more useful in our example. Now, so this is essentially an inverter driving a long wire. And this is the inverter part of the delay, and then this is the wire part of the delay. So if I want to figure out the delay to this first point between the two, I have to do the 2 components. It's R of the buffer times all of the downstream capacitors, so which is C1 plus C2. That gives me the delay of this first inverter. And then I have the delay of the wire. The delay of the wire is going to be the R of W times C2. So if I only look at the delay from N1 to N2, N1 to N2, that delay is going to be R of W times C2. And so I have to add that to the first component of the inverter delay to get the total delay. Or we can do the thing we did with trees. We can say, okay, this is the delay from the input to N1, and then this is the delay from N1 to N2. Does that make sense? And then the difference between the pi model and a non-pi model is that C1 is driven by the inverter in the first term, but it's not driven by the wire in the second term. So there's a small difference if you use a different wire model, but it's not that big. Yes?
When calculating delays, so we have to find the load capacitance. Do you usually do just the next gate that it's driving, or everything downstream?
That's a good point. You only look at the fan-out, because if we look at the model we had of a gate, let's go all the way back to this. And I kind of drew this, this division thing here, and I said, oh, this separates them. when I'm driving the input of a gate, what does the driver see? Well, it drives the poly gate of the transistors of this inverter. So it sees that capacitance. It doesn't see the capacitance, the green capacitance, because that's on the output of the inverter. And so it doesn't drive that. That capacitance gets driven by this gate itself, right? So you have the way to explain it is, let me draw another example, maybe with two of those models together. So let's say we have two of those pi models. So we have our input capacitor here, which scales S times C of the gate. And then we have our drive, so we drew it like this. Right, so this is that same model we saw. This is R over S, this is S times CP. And we have C out over here. So this is one of those models we had. Now if we draw another one of these models, like this is S times CP. So this is the self-loading of this gate. This is S times C, and this is R over S. So this is if we had two gates, say an inverter driving an inverter. So we have two parts of this. The resistance of this gate is right here. The resistance of this gate is here. The capacitance of this gate is driven by this gate. Does that make sense? And then the self-loading of this gate is also driven by itself. And then if we look at the other side of stuff, let's say this self-loading capacitance, it's driven by, well, this gate. And then the C out is driven by this gate. So you can see that there's the separation in the model here means that that first inverter doesn't see those output capacitors, either the output load or the self-loading capacitor of that second inverter. The same also applies to the input of this first inverter here, where we have a division here. Whatever's looking into here sees that capacitor. Right? So that SC on that first inverter doesn't appear anywhere if I'm computing the delays of these two inverters. Hopefully that makes it a little clearer. Now, if we add in a fan out of this, so previously we had this, and this had no fan out, right? This C1 and C2 were from the wire itself. If we now add a fan out like this, where does that get added? Well, here we have the R of the buffer times, here's the capacitance of the wire plus the capacitance of the fan out. And then we have the R of the wire times the downstream half of the capacitance, because we're doing a pi model, plus the fan out here. Another way to draw this would be the same when I did the tree algorithm of Elmore delay. I could also write it as R times the sum of all of the capacitors, which would be Cx plus, yeah, it's just look at the downstream capacitors times C. So R times all of the downstream capacitors. That's an easy way to, I don't even have to do that. Oop. Erase. Right, so that's why it's all of the capacitors. And then in the second one, it's R times the downstream capacitors from that R, which are down here. So we're just going down each stage and multiplying by all the downstream capacitors like we did in that tree example of Elmore delay, except there's no tree. It's just a single branch. And that's how we get this. So there's a component due to the, right here, this is a component due to the driver, and this is the component due to the wire. And they're both driving that C from the fan out, which is in purple. Now, what if we insert a buffer? And this is where it does this decoupling that I'm trying to illustrate. So if we divide this right here, the model has a separation here. And if we do that, what capacitance does the first green inverter see? Well, the first buffer has a delay of, it's going to have this resistance times these downstream capacitors. Which, what are the downstream capacitors? Well, first of all, these capacitors are smaller now. Instead of being Cx over 2, they're actually Cx over 4. Why is that? Because I now have a wire of half the length. Instead of a wire of length x, I have two wires of length x over 2. Each one of those two wires has half the resistance and half the capacitance. But I have this middle buffer here, which has an input capacitance and a resistance. And we see that with the orange model. So now we can redo this green times the blue is essentially this same equation right here, green times the blue, except with half the capacitance. Oops. And then we have another component, which is our buffer, the orange buffer, driving another wire that's half the length. And that gives us another term that is, Rx, or the resistance of this buffer times half the capacitance downstream and so on. And we basically do those two things and then redistribute everything. Here's the component. It ends up being this delay. We end up with two parts of the delay, and this delay is actually going to be smaller than the other delay because we broke the wire up. So because the wire is half the length, each wire is faster. But also the driver, this green driver, is only driving the capacitance up to that middle inverter, or the middle buffer. So it's driving half the capacitance. So it's faster too. But what do we do? Well, it's adding a little bit of extra delay of that orange buffer, which makes it slower. But because it's splitting up the interconnect, it makes the whole solution faster. And if you work out this formula, it ends up being this delay here on the bottom. So the unbuffered delay is here, and the buffered delay is here, and we end up seeing a better solution. Now, x is unknown here, right? X is some variable. So it depends on the length of x, which one's better. In some cases, the overhead of adding that buffer in the middle is going to slow the whole thing down. So it doesn't always make it faster. The question, though, is when does it actually make it faster? Now, there's actually another work by a professor at UT Austin right now, and he, in his thesis, he basically did work on the same type of thing we just did with exponential horn, except the question is, what is the optimal number of buffers to put on a wire? And you can do kind of a similar derivative thing and say, okay, if I divide it up into x number of segments, what is the correct number of stages? And the correct answer is you get some value. What is that value? It's actually quite insensitive to what the actual number is, but it's somewhere around a couple hundred microns in most technologies. And then what you want to do then is basically take that value, and you basically want to break up every wire, every really long wire, with that number of buffers. You can determine this value, just divide the wire length by L, and say, make that many segments. Now, actually then distribute these buffers along the wire. And this is the idea of a repeater. So you want to distribute these repeaters every L frequency along a long wire. Now the problem is you can't always put them in exactly the right place. When you do placement, either it might be in the middle of the memory, so you have to move it. So these end up not being perfectly distributed, which affects your solution, but usually it's good enough. It's fairly insensitive to a lot of these numbers. And he formulated it basically, oh, if you ignore the added buffer delay, what's the optimal? And if you include a buffer delay, what's the optimal? Similar to the other case with the exponential Horn sizing. And if you actually plot this difference, so the buffered minus unbuffered, it looks at a function like this. And that L can actually be this distance here, whatever that is for technology. What determines that value? Well, it depends on the ratio of the wire unit delay to the buffer delay. If you have a better buffer than a wire, the spacing is less. If you have a better wire than a buffer, then the wires get longer. And so this gives you a quadratic, or this equation that you can solve. This is buffer delay of, a single, your inverter or your buffer. And then this is a unit wire here, RC per unit times x squared, and so on. So that's the intuition here. There's some length where you want to break up all long wires at that length to make them smaller. Now, what is it? In general, it's a few hundred microns. I don't know, it changes for every technology. It changes on your library and your transistors and your wires. But it's okay to approximate it. Generally what will happen is if you do place and route and you see a really long wire, it's going to be under critical path. Well, what's the answer of how you fix it? Well, either you need to make the wire shorter, or you need to have the wire have a buffer on it, or two buffers if it's really long. And those just break it up so that you improve the delay of that wire. Now, I'm going to add one more thing, and then I'll answer a couple questions for midterm stuff. Actually, I'm going to skip over this, because I'm going to talk about this. I might revisit this when I talk about static timing. But I'll make one other point instead of going over the example. Let's say we have an example with a fan out of 2, because we know now that we have this and this. Every case we've seen so far is either driving a big capacitor or it's driving a long wire. There's one fan out. What if we have a fan out of this? Well, what does the delay of this look like? Let's assume that this wire has capacitance W, resistance W. This has an input capacitance, call it C1. Let's say that this one also has a resistance W and a capacitance CW, and this has a capacitance C2. Now, what if your critical path is through here? Well, what is the delay of this first gate? Now, let's also assume that that gate has a resistance R. What is the delay of that first stage? Well, it's going to be R times 2CW plus C1 plus C2, right? Just the delay of the gate, the blue thing. How can we make that? Yeah.
Are we also have resistance from the wire then?
So I'm only measuring the delay from here to here. I'm not measuring the delay to here or here yet. Yeah, so just kind of this blue, well now red highlighted part. How can I improve the delay of that gate? So I can increase the size of the resistor. That might work. There's actually another trick you can do. Yeah, go ahead, let's take some guesses.
Stick a buffer.
Stick a buffer. Where do I put the buffer?
Right after the gate.
Okay, so I could put a buffer right here, and it fans out both those. And then I could size that differently, right, from that other buffer. You could. What do you think? Before the split goes to C1? Yes. What if I put a buffer here? What does that buffer do? Well, instead of the first inverter, or first buffer, driving both wires, it only drives the bottom wire and that buffer. So what does this delay become? Let's assume it's the same size buffer. This has a capacitance of C1. Well, this now becomes R times one wire plus two of these C1s plus C2. Now, if C1 is much less than the wire, it's faster, right? Because then this first buffer is not driving that long wire. It's only driving the buffer. And it will then make this blue path, or at least the first stage, faster. What does it do to the other path here? Let's look at from here, let's say looking here. What does it do to that? Slower. I added another buffer on there. Assuming it's not a repeater and breaking up the wire, I now have extra delay on that path, and so it goes down, or the delay goes up. So I'm adding extra logic on that path to make it faster on the blue path. That's called capacitive shielding. So it's an example of taking, if you have multiple paths in a fan out, making one faster than the other by kind of hiding the downstream capacitance from it. Because that new buffer I added is driving the wire now. So we just added additional delay right here that was not there before. So this one, call this D, and let's call this D1 and D2. This delay goes down by D1. This delay goes up by D1, or D2. Now, that's what the buffering algorithms tend to do then. So there's basically three cases we want to have buffers. Driving big loads, so big capacitance, driving long wires, break them up, driving fan out, shield them. And those are the three. Now, every net is some combination of all of those, right? What if this bottom path had a really giant capacitance down here? Well, I might want to add a cascaded buffer instead of that bottom buffer to buffer it up. Or what if this wire is really long and I want to place that new buffer somewhere along the wire to improve the delay? So it's not necessarily a one or the other of the three, but it's kind of, and that's when it gets computationally infeasible to try all of them. There's a lot of algorithms that are looking for the optimal solutions. And then you have to run into the fact that you can't always put a buffer where you want. Sometimes there may only be a location, say, up here that I can put a buffer. And so if I put the buffer there, it'd make the wire longer. Sometimes that's still better, but sometimes it's not. Okay, I'm going to end this lecture there, and I'll answer questions for a few minutes for the final exam, unless you have a question on this. Why is it 2C1? Because this is the capacitance of the new buffer that I added. Right, I added this buffer, which has an input capacitance C1 here. And so you have that capacitance. Oh, you're right. You're absolutely right. It's just C1. Because the other one I called C2. Yeah, thank you. So it's just the capacitance of this fan. Yeah, this is one C2. So it's C1 plus C2 plus wire. Thank you for pointing that out. So then you can see it's guaranteed faster because in this case, this factor of 2 went away. Yeah. Okay. Does anyone have questions? Let's ignore this stuff. We can redigest it. I know you're like, I don't care, the midterm's on Thursday. What do you think? What are people afraid of on the midterm? What do you think I'll ask? then you can watch my facial expression, and I can say, oh. What do you think I'll have on the exam?
Would you give us a GDS, we can make the layout of it?
What do you think?
Dolly processing.
You guys spice code that make the CMOS of it?
Maybe, that's a good idea.
Write the code in for it in spice?
Maybe. Are there clues for any of those? I don't know. All of the above, none of the above. Okay, let's stop with that. So what questions do you have about, see, this is people that are listening on the thing don't know what I look like then. Yeah.
Do you expect it'll take a whole hour and a half?
I think you'll probably take an hour and a half. It's not meant to be long. I'll tell you it's 6 problems, or 5 problems. I forget, but I intend that you'll have like 15 minutes of problem. So if you know what you're doing, I don't think it'll take that long. If you're trying to synthesize ideas that you haven't done on the homework, you might run into problems. I'll go back there first, then you.
So you mentioned one of the problems is going to be like pretty fun similar though, right?
Mhm.
Or at least one.
Yeah.
So do you mean like will we fully conceptually from like homework examples or will we fully conceptually from lecture? To be able to do that problem?
Let me put it this way. One of the things, how do I want to answer that? I can, like one recurring theme is Elmore delay. You can do delay of different things. If you have R's and C's, that can apply to a number of things, right? I honestly don't remember if I put that on the exam, but yeah, as an example. Yeah.
So a lot of the homework, especially homework 3, was just like writing code. Is it like that we will like handwrite code on it?
So think about this, like, again, the chess opponent. What do I want to test you doing? I'm probably not going to have you write spice code, to make a waveform and put the rise and fall times. Because first of all, how do I grade that? Like, what if you have a syntax error? So think about what I want to test. That's the answer there. Yeah.
How do you plan on testing, I guess, like some of the fabrication knowledge? Because I think like,
Let me flip it. How do you think I'll test some of the fabrication knowledge? What can I do?
or I was imagining like a worst case scenario where you're like, you start with the silicon wafer, draw the step by step of like chemical wafer deposition, and like this stuff, but like,
Yeah. I have to see if the printer's still open. No. I mean, that could be like, if you have two layouts, what happened between these 2 layouts, right? But remember, I can't do it too generally because I have to grade 82 of them. So, yeah.
So you have to make it end well only the CMOS, right? We're making a cross section.
Or for the PMOS. No, so the answer is when you have NML. It depends on what the layout shows. There's cases where you may not have. What if I have a PMOS and it's not an or a transistor is not an NML? It's not a PMOS. It's an NMOS. So, yeah, I could have a layout. Let's say, and there's no NML in it. And I say, what is this? Well, it's an NMOS and an NMOS, right? Yeah.
So we don't put anything that means P substrate.
You can assume most of the examples and stuff I'll do will have a P wafer. Yeah. And if I do things that are different, I'll state the assumptions, right? I could say, oh, that could be an example. What if I have an N-well process? Those exist, where you have, a P-well process, where you have N wafer and a P-well for the NMOS. That exists. SOI has 2 wells. You have a P-well and an N-well, and you draw both of them. SOI is silicon on insulator. So the idea would still apply, right? Actually, I think in the, it doesn't exist in SkyWater, but it does exist in other technologies. Yeah.
if you give us the layout wrong, we're going to give us the color code as well.
If I give you a layout, I'll give you color coding. And if you can't see a shape, you want to ask me something, you can say, is this here? I'll say yes or no. Like, we had people had problems with the contacts, for example. You could say, is there a contact here? If you ask me a yes or no question, I'll answer it. I won't answer, what is this? Yeah.
I don't know if it's already said, but is there like multiple parts to the problems or you just
Yes, there's multiple parts to the problem. So by saying 6 problems, there's 42 parts. No, I'm joking.
could it be like a small conceptual portion like part A is like, oh, wait,
So-
something about the
So,
process.
so I'll tell you this, I try to make multiple parts to make it easier to grade, so if you make an error, it doesn't flow through to the rest of the problem, right? Because otherwise then I have to do partial credit on all the later problems. So that's something that I'll frequently do. Yeah, go here.
How lenient are you on partial credit?
Well, how lenient am I on partial credit? We'll see how badly people do. No.
So speaking of the not letting that problem cascade, so like if you get a number wrong in part A and part B depends on it, would you get part B wrong as well?
I try to, so if you get part A and part B depends on it, I try to not have it cascade, but I can't always compute all of the dependencies. So it depends. I'll try not. And you may have to do a regrade if there's something like that, if you used a value, but again, I try to make them somewhat independent.
Like as a rounding, what do you want us to round to?
Rounding, I mean, you have a calculator, like, be reasonable. Don't give me integer solutions, except with 4, that's fine. Actually, I will say pay attention to units. Like, I know if you just look at your homeworks and you didn't work out units, look at femtofarads, look at picoseconds. Kind of understand how units scale, right? Elmore delay, R times C, what units are those? Here's a way to think about it. What are the units? Let's say R is in ohms, C is in farads. What unit is delay? Seconds. Remember that. Yeah, if you remember that, you can figure out everything else because they cancel, right? And you can scale it appropriately or not. Yeah.
Should we put that scaling on or should you choose?
I give you the scaling. I give you, I think, I forget, atto through kilo. So, yeah, I give you all those. So atto is, way too small. I go 1 beyond what you need, right? Because I don't think we use kilo ohms, I guess. But, all right. Yeah, just do some studying. Don't be afraid to go to Hodder's office hours. He knows all this material as well as I do. You can have questions. I advise you have questions besides the ones on the homework. Like, try to make example questions and see if people can do them. You can post them in Slack. I'll answer them. If you come up with an example question and you get stuck on it, I'll answer it. So, like you had a few examples of like, CMOS gates. Like, there's many CMOS gates, right? Look at the library. You have all the different functions. So that's something. All right. Don't worry too much. We have 3 exams in the class. So midterm 1, midterm 2. So this one's a little less stakes than prior years. But then I guess the other thing is, most people are getting 100 on the homework. So I expect people to turn the homework into 100. So all the rest of this stuff is 80% of your grade. So I think this one was 20%, and the final is 35%, if I don't remember correctly. I think that's what it was. It's on the syllabus, to be clear. Or was this one 25? 25, 25, 30. Yeah, thank you. And in terms of the midterms, this one covers through I mentioned through lecture 6. The next midterm will basically focus on lecture 6 through static timing or whatever I get to, and then the final will be cumulative. So I could throw a couple questions on the old stuff, but I'll probably have the next midterm focus mostly on that stuff. But you will see this stuff again on the final. So, all right. Okay, I'll hang around for a few minutes if people have questions. Oh, are you Chris? Yeah. Okay, yeah. I'm going to stop by at the end of this exam. You extended time? I'll stop by, so it won't be until we're done here. So if you have questions, you can save until the end.
Yeah, I was going to ask, could the proctor send you a text?
Yes, they can do that too. They have that information. But I'll definitely stop by. Okay, yeah.
So there's a very same question. Is that the most recent homework I actually turned in completely not my actual homework. And the complication is that I'm not sure if I saved it because I don't have these things to check. I guarantee I've done that. Also, like run through. I think I have a little bit of my English. But if the solution is just like eat it, that's
There's not much I can